Recall that before we talked about matrices, we were talking about systems of two equations of two unknowns. This could look like 5x plus 10y equals 4, and x minus y equals -3. After exploring matrices, we see that we can express this system as a matrix times a variable matrix, and setting it equal to another matrix. Here we call our matrix that was composed of the coefficients of the terms our coefficient matrix. Looking at our system, we see that there are two matrices that include numbers and one matrix that includes variables. Often, as we see with word problems, we might introduce the variables themselves, so the names of which letters we choose for the matrices themselves might be not as important as the numbers found in the system. For this reason, sometimes we introduce an augmented matrix. If we look at an augmented matrix, we can immediately see that the number of rows tells us the number of equations of the original system. And the number of columns, -1, because we don't want to count that extra augmented column, is the number of variables of the system. Given an augmented matrix, we can convert it to a system, or vice versa. In the context of solving a system, some matrices are easier to read off a solution. For example, the augmented matrix 1, 0, 0, 4, 0, 1, 0, 3, 0, 0, 1, 2 corresponds to the system x equals 4, y equals 3, and z equals 2. Or 1, 0, 1, 0, 1, -1, which corresponds to x equals 1, y equals -1. This form of ones along the diagonal and zeros elsewhere, except for this last augmented column, has a special name. We'll refer to it as a matrix that is in row-reduced echelon form. And it could be for a system of two unknowns, three unknowns as we were shown, or in more general case, ones along the diagonal, 0 everywhere else, except for our augmented column.